Hi, my name is Leigh Hainig. I am a PhD student at Carnegie Mellon University in their Engineering and Public Policy program, and I will be presenting on the equity implications of high electric vehicle penetration rates for public chargers in emergency evacuations. Electric vehicles are expected to reach higher penetration rates in the US, with California mandating that 100% of cars sold in the state have to be electric or other non-tailpipe emissions technologies by 2035, and several car companies committing to going fully electric in the next 10 to 15 years. Given the expected increase in electric vehicles, there is going to be a greater demand for public chargers as more people buy electric vehicles that do not have access to a consistent off-street parking spot where they can install a private charger. Trout et al. In 2013 explored what percentage of households would require public charging versus would have the ability to build out private chargers in their house. They found that although close to 80% of homes have a parking spot, only 22% of homes in the US are capable of installing a charger, only 22% of vehicles. And the reason for that is that some homes have multiple vehicles, some homes are rentals, and therefore the person living there cannot install a charger, and some parking spots don't have the ability to connect to the grid or build out a private charger. Therefore, there is going to be an increased need for public chargers as penetration rates increase. There's also an equity component to the distribution of public chargers, because at the federal poverty line for gross annual income, only about 15% of households would be able to have charging, while at $100,000 in gross annual income, close to 75% of households would have the ability to charge privately. So access to public chargers is going to need to be greater for low-income households. Natural disasters also impact public charging, because during a natural disaster or a rare event such as a fire, hurricane, flood, or winter storm, there may be a need to evacuate, and sometimes there's only a few hours notice during an evacuation. When there's a need to evacuate, there's going to be high demand for public chargers as people need to fill up so that they can get out safely. However, in those same natural disasters, there can be power outages, which makes a greater amount of people have to rely on fewer chargers. And this high demand coupled with fewer availability can cause safety concerns when there's a high EV penetration during a natural disaster. We have built an optimization model to find the best and minimized location for chargers. And so the first part of the model involves optimizing the location and the amount of chargers at each station, constrained to having each station have similar wait times to the near population centers, and then also having a station be at a similar distance to each population center so that people are not left far from a public charger or with not enough public chargers in their area. We then evaluate the cost difference between the least cost model and the more equitable charger distribution, with the least cost model not necessarily providing equal wait times or equal distances to a public charger. And we evaluate the differences between the least cost and more equitable distribution for evacuation capability. In this model, a charging station is represented by big N. That is a cluster of chargers that are together, and a charge supply is the amount of charge that a charging station has. So if a charging station has 2 chargers, it has less of a supply than a charging station that has 7 or 9 chargers. We use San Diego as our geographical scope for this model. San Diego has 38,000 population centers, which are the centroids of census blocks given by the American Community Survey, and it has a total population of 3.34 million people. Specifically, we use Coronado Island in our preliminary analysis because it is an island with 16 population centers and 25,000 people. So it creates a nice contained problem to show the feasibility of our model. In our model, we assume that 100%, it is a 100% EV penetration scenario. We also assume that of the EV charging demand, 50% of it needs to come from public chargers, with the rest coming from private chargers. And we assume that the public chargers we are optimizing are level 3 DC current fast chargers. We also assume that each charger is unused 60% of the time to account for nighttime and gaps in the day between charging. And we use the Department of Transportation vehicle registration to find that there are 2.5 million registered vehicles for the 3.34 million residents. Given all of our assumptions, we find that there needs to be one public charger per 1,300 people. We assume that every single station is supplying some amount of charge to every single population center. However, the amount that it supplies is weighted by both the demand of the population center and the willingness multiplier between each station and each population center. The willingness multiplier is a Gaussian of the distance between each station and each population center. So as you can see here, station 1 has a larger willingness multiplier with population center 3 than with population center 2. This is because it is closer. So we assume that that population center will be more willing to go to that station. However, population center 1 has a larger population than population center 3. So although it's further away because it has a higher demand, station 1 might supply the same amount of charge to both of these population centers. Our first constraint is that the total supply of charge must be greater than the total demand for charge. This is so that all demand in the system is met. Our second constraint requires that all of the willingness multipliers sum to 1 so that there is not more supply in the system than there actually is. Otherwise, a station may be oversupplying the nearest population center demand, and this would cause greater wait times because there would be more demand in that area than the station can actually supply. We also require that all stations be on a road. This is just a feasibility constraint because vehicles need to access it. We first use a genetic algorithm in MATLAB to place stations on the map in fairly good locations, and then we use interior point to optimize both the location of the stations and the amount of chargers needed to be supplied at that station to meet the demand and the constraints. After this, we move the charger stations to the nearest road using ArcGIS. In our preliminary analysis using Coronado Island, we run the more equitable optimization model with the constraints, and we find that the stations spread out to avoid oversupplying the center. However, when the entire county model is run, the stations move slightly inward because they're getting external population data from around the island, which pushes the ideal location slightly inward. Our preliminary analysis has 16 population centers represented by the blue dots with 6 stations, and each of the stations has 2 to 7 chargers. As you can see, the area with higher population has more chargers at each station to meet the demand in that area. When we loosen or relax the first constraint, we find that the stations all cluster in the center between the different population centers, giving fairly equal distance, but it's not particularly ideal for any. This is the least cost, and it only requires 19 fast chargers to meet the demand of the system. However, there might be long wait times or further distances. In the more equitable model, where we apply constraint 1 on the right, you can see that the chargers spread out and there needs to be 24 total chargers across the 6 charging stations. So that represents a 26% more demand for chargers in the more equitable model. If we instead relax constraint 2, which is that the willingness must all sum to 1, we find that the charging stations are still fairly spread out, so that distances to each station from population centers would be similar. And this is like an equal distribution of chargers. However, in this case, in the center of the island where there's a higher density of population, the wait times would be higher because there are more people per charging station, despite having a equal distance between each population center and the nearest station, compared to the more equitable distribution where there are more stations around the population center so that people have both similar wait times and similar distances from each station. And the more equitable distribution, it requires 10% more chargers than an equal distribution in distance. We run the full county problem, and then we move the stations to be on the road. And as you can see, there's a station that went across the border in Mexico, and then when it was moved to the nearest road in the county, it came across the border. So some limitations to our model. The algorithm often tries to service more than one area with a given charger. This is pretty ideal, except when there's a physical barrier between the two areas, such as a mountain or a river, where it's not actually very practical to try and service both with a single station. When there is a very unpopulated area, such as a national forest, the willingness multiplier, the gradient of it vanishes to 0 in that area, and it becomes difficult to solve. And sometimes chargers get placed on infeasible places like mountains or bridges where it may not actually be practical for people to go there to charge, such as in the picture on the right. And existing public chargers are not yet taken into account in the model, but should be because there is not actually a need for chargers there. So next steps, we are going to make the willingness multiplier be a factor of road distance as opposed to absolute distance as the crow flies, because that way when there's a physical barrier, it's not accounting for the absolute distance. Instead, it actually accounts for how far it would take to go via road to get to a station. And we also are going to weight the demand by household type instead of just assuming an even demand across population, because houses with garages can presumably install more private chargers and therefore have less of a demand for public chargers than multi-unit homes or apartments where people rely on a inconsistent rotation of parking spots. And we also need to test out different EV penetration rates, not just 100%, to see how things differ. And we need to run the evacuation simulations to see how the capabilities compare between the least cost and more equitable EV charging distribution in an emergency scenario. I would like to acknowledge the National Science Foundation, GRFP, for funding this, as well as Sven, Harry, Tanmay, and Rachel for helping formulate the math, as this optimization project came out of a group project. And also Destiny Enoch, Corey Harper, and Jeremy Mahalik for feedback on the model and all the assistance. These are our references. Thank you so much.